thing.
Does that mean I can like?
Hey Ryan, can you close the blinds?
Is it possible to close the blinds?
Yeah.
Oh, yeah, close the blinds because we can't see.
Or if I like raise my hand and you're facing the board, it'll
Holy
just...
crap, I have such a headache.
I'm sorry.
Do you
Okay,
have to the thing
so,
when you're here?
I gotta go! I gotta start! Now!
We're behind.
Hold on. What am I doing? I'm talking about physics and stuff.
We haven't
Yes.
done Einstein's equation.
Yes!
Okay, what the hell?
Yes!
We're gonna
Okay,
learn
alright, here we go. Okay, so what I was going to lead with, although no, I'm kidding. My head does really hurt, but that stuff will take so long. I really just like need to snort something. Not that I'm going to do that, but okay, so what I was going to say was I got really confused last time, and I did exactly what I promised. I figured out exactly what I was confused about and put it in your homework. So you have a third homework problem, which is exactly what I got confused about last time. So you're going to sort it out for yourself. I did check it and it all makes sense, and I kind of walked you through it. But I was going to have us all say thank you. Actually, we can say it because since she's not here, she will watch the video. So let's all together say thank you, Adria.
Thank you, Adria.
Because of you, we have the third homework assignment. Third homework problem. Okay, all right, here we go. So I'm going to be kind of in a hustle today because we're going over, and where was I? Yes.
Three pages left.
Nope.
Yeah, you read them.
Yeah, here we go. Okay, so we have so far beaten our metric into the following form. And remember, our method has been impose spherical symmetry, and imposing spherical symmetry let us make a lot of simplifications, and we did this S2 foliation, got rid of a lot of cross terms, lost dependence on theta and phi, or certain dependence on theta and phi, and then we used coordinate or gauge transformations to simplify things, and of course a part of that is where I got confused. And then the final step, which is what we're going to do today, is actually use Einstein's equation, which we in trace reverse form with vanishing source is just r mu equals 0. So where we got to at the end of all of this is the following form. We got a diagonal metric. Yes, okay. Where we are writing the time piece of the metric, and I'm writing this in terms of a line element, as an exponential of an unknown function alpha, 2 times alpha just by convention, but the unknown function alpha of r and t multiplying with dt squared, and then similarly an unknown function beta multiplying with dr squared. And then, of course, we've got this nice simplification from coordinate changes that the angular piece just takes the standard form. And so right now we are sitting at 2 unknown functions. Okay? Very quickly, Ryan Short, where are you, Ryan?
I'm here.
Ryan, why do we write these as exponentials?
So that when we define functions that we can use, we use square roots. And it's
Well, they didn't start out as exponentials, but I made them exponentials. Why did I? Oh, the other Ryan wants to.
Yeah.
They're all positive?
Yeah, if you put the unknown function in an exponential, this whole term, this exponential, is necessarily positive. The very last thing I made an argument about last time was that the overall coefficient of dt squared should be negative, and the overall coefficient of dr squared is positive. So those exponentials are just going to enforce that for us. That's the main reason they are there. Okay, so here we go. So step 3, Einstein's equation. Okay, so if we put things into Einstein's equation, what you would do is what you know how to do. You could go into the Mathematica package, the great package. You could enter this as your metric. albeit it will have unknown functions, but that's fine. And then, and of course you define your coordinate vector, so it knows that t and r and theta and phi are coordinates. And then you just simply ask Mathematica, what is the Ricci tensor? And it will spit out the Ricci tensor, but of course the Ricci tensor it's going to spit out is going to involve derivatives of these unknown functions. Because you didn't tell it what the function is. And to get the Ricci tensor, it has to take derivatives of the metric, etc., etc. So what you're going to get out of the Mathematica Great package, if you plug this in and ask it to calculate this, is a set of differential equations. Essentially one equation for each component of the Ricci tensor. Okay? Now, many of those are going to be zero identically. Okay, you won't even have a left-hand side. And the only ones that are going to give you non-trivial expressions turn out to be the time-time component, the radial-radial component, the cross component, RTR, and then the two angular components. So when you calculate, when you have the package calculate this, then you write that down and say, Einstein's equation says it has to equal 0. That's your differential equation. I mean, it's an equation, it needs an equal sign. Okay? So the left-hand side would be the output of Mathematica that it calculates from that, and then the right-hand side you put as 0. For the other components, the package is going to give you 0, so setting it to 0 doesn't really give you very much useful information. Okay? Now you might notice there's a cross term there. It happens. Just because you have a diagonal metric does not mean that the Ricci tensor needs to be diagonal. Okay? All right, so now we're going to work with some of these things, and we're going to start with the RTR result. And of course this is just getting the information from Mathematica. If we plug this in, we're going to find 2 over r d beta dt. Okay, and we set that equal to 0, which immediately tells us what?
Beta's constant.
Which immediately tells us
It doesn't depend on t.
beta doesn't depend on t. It doesn't have to be constant, you're close. It can depend on r. Okay? So this tells us that beta only depends on r. It can't depend on t. Okay? Then, if we, so this is what we can do. We can take, and I think I've written it this way. Then what we can do is we can take this form of the metric and simplify this term by, and this is what we're feeding into Mathematica, now say beta only depends on r. Because we know that's true. And go back and feed this back into Mathematica. Because it's going to give us different components of the Ricci tensor, which are typically going to be simplified versions of what we originally got. Because basically all the terms with derivatives with respect to t of beta are going to be gone. So if we do that, and we look at the theta-theta term, then we're going to find an expression of the following form. And as you follow what I'm saying, and it includes going back to what we did in the first lecture, I am going to give you a homework problem where you are going to derive an analog of the Schwarzschild solution in slightly different situations. Okay? So you do want to at least, kind of follow the narrative of what I'm doing, but expect that in the homework you're going to actually go back and repeat some of these steps. You won't have to repeat them all, but you'll have to repeat some of them. Okay, so plugging this in, minus the alpha dr minus 1 quantity plus 1. Okay, and again, this is what you get after you go back and you say beta only depends on r. I set this equal to? 0. Good. And to get something useful out of this, what I can do is take a time derivative of it. And by the way, I say this before, and I'm going to say it again, like, none of this is something you would just figure out on your own in, you know, a day. Like, you know, people spend a lot of time deriving the solution. Well, Schwarzschild spent a lot of time deriving the solution. Many people have perfected the presentation of deriving the solution. You can't guarantee that Schwarzschild derived it in this way. But I don't want you to get like, I would have never figured out to do that. Like, who the hell, you know, decided to take a time derivative of r theta theta? I wouldn't have. Don't worry about it. Just see the magic that happens. All right, so I'm going to just write down what we get from the time derivative of this. And in a moment, you will see why we did it. And then we have the derivative of what's inside. Okay? Take the derivative of something that is 0. You, of course, still get back 0. The stuff in the parentheses here is just the stuff in the parentheses here. I'm just letting the time derivative act on the exponential here to generate this term. And then on the second one, I just get this term and the derivative acting on this. What's that term?
0.
0, exactly. You can reorder the partial derivatives, hit the beta with the partial t, and we know that that is 0. Zero. Yeah, d beta dt is 0. So this whole first term goes away. The first term here goes away, and then we're just left with that dinky little part. And so we have minus r e to the minus 2 beta dt dr of alpha is 0. And what this tells us is that alpha, okay, so the mixed partial of this function of r and t is 0. This isn't going to vanish because of this coefficient vanishing. It's going to vanish because this vanishes. All right. So if the mixed partial vanishes, what can you tell me about the form of the function alpha?
It's one or the other.
It's a function of r or a function of t.
Or
In addition,
Yeah.
it's a function of r plus a function of t. Okay, I'll write it and then you can just go, oh yeah, the mixed partial, that would vanish. So we can write this as a pure function of r plus a pure function of t, plus a constant if we want, but constants aren't going to get us anywhere. Okay? So everybody understand why the mixed partial of that sum vanishes? Okay? All right. If we now take this and we plug it into our form of the metric that we've gotten so far, we now have that. Okay? And because you could just never get too much of a good thing, what do you think we're going to do with that guy?
We do a transform coordinates again.
Yeah, we're actually going to play the exact same trick we played and got very confused on last time. We're just going to redefine t. So if we redefine t to include that problematic factor, so technically we would integrate e to the gt dt in order to do that. So coordinate transformations are what is the new coordinate in terms of the old coordinate, but because we want to get rid of dt specifically, we need to do this like so. But that integral expression just gives us exactly that dt prime is e to the g of t dt. Okay? Take the derivative of this side, take the derivative of this side, the integral goes away, you're left with that. Now when you square this, you get this squared, and that's exactly this term. So if we write this in terms of the t prime instead of the t, this whole term just becomes dt prime squared. And what are we going to do with those primes? Drop them! We don't want to carry around those primes. Okay? So by choosing our coordinates and using a couple of the Einstein's equations and choosing our coordinates carefully, our metric is now taking the form like that. Okay? Everybody on board? I'm going to erase this.
Also,
Beta of R.
yeah.
Oh, yeah, sorry. Thank you. And now I'm yelling at the board and hurting my ears. Okay, now I want you to take a moment in time to appreciate a very interesting feature of this metric. Don't make me pick a card. Come on.
Everything's dependent on only R.
Yes! In particular, it does not depend on t. The geometry making only an assumption of spherical symmetry and exploiting coordinate redefinitions, which don't change the geometry, you get to the conclusion that you can pick a coordinate system for which this geometry does not change in time. Now, folks, that is not trivial. Because, for example, you could have an object that is spherical which changes in time. You know, maybe it suddenly grows or it steadily grows. Okay? So it's, and I'm talking about its volume, I'm not talking about adding mass to it. Okay? Even if this thing is changing in time, as long as it maintains spherical symmetry, for a point outside of it, we can get a geometry of this form that is time independent. Okay? All right. Now, there is actually an interesting feature that you run into when you try to make things time independent in GR, and we're actually going to run into it. What you will often find is that for many geometries, you can exploit coordinate transformations to get the metric to be time independent, even when things are literally doing stuff. Okay? But one of the things that you find when you do that is that the metric you write down that's time independent doesn't actually apply to the entire space. It only applies to a region of it. We're actually going to find that this is true as we continue investigating this solution. Okay? But that won't happen today. It'll happen in another discussion. Okay, so we have gotten to the point of time independence. And a time-independent space is called a stationary space. Okay? So this is an example of a stationary space. But, I don't know what that vibrating is. It's making me happy. All right. So, also, it is invariant under t goes to minus t. Now, those two things do not have to imply each other. So for example, I could give you a metric of this form. I'm just making some shit up, it doesn't really matter that much. Okay? That metric is time independent. There's no t in there. And when I say time independent, I'm looking at these coefficient functions. Okay? However, this metric is not invariant under t goes to minus t. Because what happens if I send t to minus t?
That term flips.
dt flips. So this metric picks up a minus sign when I reverse the direction of time. This metric does not change sign when I reverse the direction of time. It doesn't have a cross term. Now that sounds like a stupid, boring mathematical observation that you really don't care about, right, Jonathan? Yes?
Yeah.
No, that's where you disagree with me.
Okay, no.
Okay, but there's actually a very practical, no, I make this point because this is actually very practical in finding solutions. If you have a star that's sitting there, the geometry you might expect would be something like this. Because if the star is just sitting there, you can run time forward or run it backwards, the star ain't going to change. The geometry ain't going to change. Okay? But consider a star which is spinning. It's spinning at the same rate. It's not speeding up or slowing down. If I look at it now, I see it spinning. If I look at it 10 minutes from now, it's still spinning. The geometry is time independent. But if you reverse time, what happens? It spins the other way. Okay? So this is actually of incredible practical importance because stars do spin. We will consider the spinning version of this solution in due time. When we consider the spinning version, one thing we expect to encounter is a cross term in dt something. It turns out to be the dr dt cross term. Okay? But the solution we're going after today is truly stationary. It is independent of time. It is also independent under t goes to minus t. And together we call these static geometries. Okay? Questions about static geometries? Good. Pressing on. All right. So we've got ourselves down to this really nice time-independent form. Time to go back to Einstein's equations and see if we can exploit some more terms. Okay, so again, we can now take this form of the metric, shove it into Mathematica, take what Mathematica cranks out for the Ritchie tensor components, and coming back to the new form of those, if we look at the RTT, we find an expression of the following form. Oh boy, this is where this thing's going wrong. That's F and theta, yeah, good. And we set that equal to? 0. Yes, nice, okay. And because it's going to turn out to be useful, although it might not be obvious why, we're going to go ahead and write down what we get for the RR component, where RR does not stand for Ramon, but rather stands for radio. If you went to enough string theory lectures and talks back in the day, it was so weird because people would always talk about the RR and the NS and S. That was even weirder. But anyway, not so much talk about that these days. I'm doing what's called vamping because I'm spending a lot of time writing, so I'm just running my mouth so you don't get terribly bored. But, you know, if I had jokes I could come up with, I would do that. All right, here we go. Okay. All right, so this literally just take the metric, shove it in, get the RTT and the RR components of the Ritchie tensor, or the TT and the RR components, set them equal to 0. But now we can get something useful out of this. If I take the term in parentheses from the first expression, and I add to it the second expression, what should that equal? I mean, what should it equal?
0.
It should equal 0. The second expression is 0. The first expression is 0 as well, but it's 0 because the thing in parentheses is vanishing. It's not 0 because this thing is vanishing. Okay. So this plus this is 0, but if you actually plug in all of these things and all of these things, the expression that comes out of it is 2 over r df dr plus d beta dr. Which immediately tells us that df dr is equal to minus d beta dr. Yes?
Which of those terms gives you the df/dr?
Say it again?
Which terms give you df/dr?
First three terms on either one.
In the top and bottom.
Yeah. So I'm sorry. There's some steps here that I'm leaving out. So you add all of these things together, and then you factor out overall df/dr.
Wait, what?
So you're going to get, okay, so let's see.
But you can see just like those first two cancel.
So wait, these, okay, you guys can do this to me. These cancel, these cancel.
Those cancel.
Oh yeah, no, I wrote it down wrong. Yeah, no, yeah, you're totally right. That's enough. Sorry. My eyes cast down to the next line. You're totally right.
Okay. Sure, blame on the eyes.
That's why we're sitting so close.
I'm telling you, man, you guys are sweating me. You know, it's like, I'm going to make you guys, I don't know what I'm going to do.
This is
Screw
what
you guys.
feels like
I'm
these
just going
holes
to
are
see
cornered.
Okay. So this tells us that if we can figure out f of r, then f of r is going to be minus beta r plus potentially some constant. Okay? And so then we can take that and we can return to ds squared. And we can say, okay, so instead of f, I'm just going to do everything in terms of beta. So my f becomes a minus beta. And then we get the contribution from the c. And at the risk of sounding like a broken record, what are we going to do with that?
Coordinate change.
Yeah, we just do a coordinate change, absorb the c into the definition of our time, and so this can become a dt prime squared, which we will happily forego the primes and just call it dt squared. Okay. I mean, you might notice every time I do this, I've got either a constant or a function of the coordinate that the d is of. So if this was a function of t, dt squared, I can make the redefinition of t to make that function go away. I obviously can't do that with a function of r. Like I can't make the t go away. I mean, you could try and play the trick here, but if you tried to play the trick here, you'd have to be really careful because this term would change and that term would change. So we've got to be really careful what we do with r. Do a lot of tweaking with t, but r appears in too many places. Okay? All right, and then last but not least, if I take all of this and head back to the theta-theta equation one more time, and I'm going to regret this. No, I'm good, we can do this. Heading back to the theta-theta equation one last time, I get e to the 2f. Wait, no, yeah, no. Oh man, yeah, it's beta. My notes are not right, but it's beta. Yeah, e to the 2 beta minus 2r, and I'm going to have to correct my notes. I hope I remember. If you look at my notes, I might have f's in some of these places, but I'll try and remember to correct it. Plus 1. So that's the r theta theta term using, our new form of the metric. Okay. Set that equal to 0. And what we find is that this thing can be written as d by dr of the quantity r e to the minus 2 beta. But by the way, I mean, before I even work the magic of this step, notice we got one unknown function of one variable. Like, we have gone a long way in solving this. What did we start with?
It's like 4 unknowns.
How many unknown functions?
2.
10 unknown functions,
Oh, yeah.
the components of a symmetric 4x4 matrix. 10 unknown functions of 4 coordinates. How little? And now we've got 1 unknown function of 1 coordinate, so it's not bad. Okay, so we got this equation. We can take this thing and rewrite it as that. I'll let you prove that to yourself on your own time. Being equal to 1. And that tells us that, of course, this quantity right here is linear at best. Okay.
Beta.
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 God damn it. I know. I'm doing myself a disservice looking at these stupid notes. I should just figure all this out on the fly. I don't think I could ever do that. Casually manipulating this, dividing the R through. Looks like that. Leaving now the form of our metric to be e to the minus 2 beta, which is the leading term, is just 1 plus c over r to the minus 1. Yeah, go ahead.
Why is your RE to the 2 beta not negative 2 beta?
Oh, wait a minute. Hold on. Oh, no. No.
I'm sorry.
Shit. God damn it. All right, so yeah, this is the problem. Okay. This is an F. And this is an F. Yeah, you'll understand why in a minute. And this is an F. Yeah, I was looking at this and I started like immediately shuddering when I wrote that. Because I was like, it looks right, except that it's totally wrong. And this is an F. And this is an F.
So is the metric at the top still a beta?
Yeah, no. The metric is fine. The metric is fine. Okay. This step was done in terms of F, but remember that F is minus beta. So we can switch back and forth between F and beta if we want. Okay. I don't remember why I did this in terms of F. Sorry. We probably should have just done the whole thing in terms of beta, but nonetheless, having done this in terms of F, getting to this conclusion, if F is equal to minus beta, then e to the 2 beta is 1 plus c over r to the minus 1. Go ahead.
You didn't answer my question.
Oh, sorry. Go ahead.
Why is the e to the 2f not negative 2f? When it's equal to r plus c, r e to 2f.
Oh, yeah.
Without changing the beta.
No, oh, sorry. Yeah, that's not supposed to be negative. Sorry. My bad. I don't know why I put a negative there. It's not even in my notes. I'm just like literally like.
From F to beta?
Say it again?
Maybe because you flipped from.
Yeah, maybe because I switched it to beta.
Okay.
Yeah, but yeah, that's supposed, like literally rewriting this equation, you can rewrite it in this form, so you can check that.
Yeah.
Okay. Okay, so that in this expression now makes that positive and that the inverse. Okay, sorry about that. My bad. You guys should just get another teacher. Okay, all right, good. We're doing not great, but not horrible. We've done worse. Okay. Now, this should start looking, if memory serves you correctly, a little familiar. Okay? In fact, our next step harkens back to the lecture that we had right before spring break, of which I know you all remember everything. But I will remind you, in the lecture before spring break, actually it's before the lecture before spring break, but in the lecture where I showed you how the Newtonian approximation emerges from GR, okay, I showed you how Newtonian gravity actually comes from GR in certain limits. Okay. In that process, we made an identification in order to get everything to give us Newtonian gravity, both in terms of how you create gravitational fields and how gravitational fields influence the motion of objects. And in that, we had to make the following identification, that the theta-theta component of the metric, which is minus 1 plus 2 times this function here. That function there is just, we just identified with the Newtonian gravitational potential, minus gm over r. Okay? But in the present context, that just tells us that the theta-theta component of our metric we should identify as minus 1 minus 2 gm over r. And that's important because our solution has an arbitrary constant, c, that we need to determine. And so what we can say is, in order for this solution to reduce to the correct result in the Newtonian limit, c needs to be what?
Negative 2 gm.
Yes, negative 2 gm. Okay? So our final solution is that. This, of course, is the Schwarzschild metric that I started the lecture before spring break with. Okay, we just wrote this thing down and then we explored the geodesics. We talked about motion in this geometry, stable and unstable orbits, the precession of the perihelion of Mercury as determined by this. That's where it came from. Okay. Now, this geometry described by this metric in these coordinates, these are of course called Schwarzschild coordinates. Okay, is something we're going to play with for the next several topics. This seems like a lot of language, but I'll give you a preview of something. We are going to find that these coordinates are not the best suited to exploring this geometry. So we will end up talking about at least 2 more sets of coordinates. Now the important thing is that whatever coordinates we adopt, they will no longer be Schwarzschild coordinates. They're still describing the Schwarzschild geometry. So there's this true space we're dealing with. We're just going to look at different coordinates to describe it. So when I write down this form of the metric, that's this geometry in these coordinates. And then we'll see variations of that later on. One more thing to say before we move on is there is obviously a special value of r where stuff gets interesting, and that's when r is equal to 2 gm. So r equals to 2 gm. We call the Schwarzschild radius. So if I say the Schwarzschild radius, I'm talking about that quantity 2 gm. That's going to play an important role. And then last but not least, if I go hella far away, I take r to what? Infinity. What happens to this term? It becomes minus 1. What happens to this term? It becomes 1. And what does the metric become? It becomes the metric of flat space in spherical polar coordinates. But that is exactly what you expect. If you go so we're describing the geometry of a universe with one round object in it. Well, if you go very, very far away from it, you expect to see flat space. Okay? So the Schwarzschild geometry described by this metric, and again, I'm going to add some words, but we've got to be precise. This is the geometry around a spherical source in an asymptotically flat space-time. Asymptotically flat just means if you go infinitely far away, the space becomes flat. In your homework, you will do a different version. You will actually go to an asymptotically constant curvature space-time. And that will change the form of the metric. Go ahead, Ron. Well, you got to go faster than that.
Never mind, sorry.
All right, good. All right, no questions. No, yeah, Caleb.
Isn't that last term an r squared? So wouldn't that make our, like at infinity, wouldn't that make this not flat?
Well, no. If I say what is the metric of flat space, it is minus dt squared plus dr squared plus r squared d omega squared. That's the metric of flat space. I mean, you're using spherical polar coordinates, so if you go off to infinity, this term is describing the area of this infinite shell. It should be infinity. Like there's, yeah, it's weird, it's going to infinity, but that's perfectly reasonable for what you're trying to do.
Okay.
So let me put it to you this way, Caleb. If you take the r goes to infinity limit, and this reduces, and then you just transition from polar back to x, y, z, t, this will just become minus dt squared plus dx squared plus dy squared plus dz squared.
Okay.
And then you know, there's no confusion.
I remember my question.
Yeah.
That's only for outside of the mass, right?
This is exactly the next page. We go inside. Okay. Other questions? Let's jump in. All right. So, and again, I hate going this fast, but you know, there's going to be a video and notes and homework. But I really want to be able to get to the topics that we are going to cover. But for many of you, this is going to be the best part of the course. Like, this is where it gets fun. We haven't even talked about a black hole yet.
It's already fun.
Yeah, well, you keep telling yourself that. Okay, interior solutions. All right. So we're going to study interior solutions for one reason and one reason only, and that is because we ultimately have to kind of get to this conclusion that black holes form, and we're only going to get that by looking in the interior. I'm going to do a very, very, very quick review of how this story plays out in electromagnetism, because there are certain things there that get replicated. So going back to E&M, we did, for the exterior case where the mass density is, or where the charge density is 0, we solved that, and we found that the solution for the electric field outside, which by spherical symmetry only depended on R, took the following form with a 1 over R squared dependence. Okay? And then when we go to the interior, when we go into the interior, we now have to reckon with the fact that we are in a region where the charge density is non-zero. Okay. You're inside of the charged object, so you're where the charge is. Remember, the differential equations are describing what's happening at your location, and if you're inside, you're in the charge. Okay, so we want to find the interior version of this solution. And again, assume spherical symmetry. Now, to set this up, I'm going to assume that my object has an overall radius of capital R. So we're talking about a solution when R is less than big R. Okay? But before I can give you any, you can even start finding an interior solution, I actually have to give you one more piece of information. You couldn't even start here. What's that piece of information?
Charge density.
Yeah, I have to tell you, is it uniformly charged? Is the charge like more dense at the center and then it kind of gets less dense? Or is it more, you know, you have to know how the charge density is distributed. Okay? So I'm going to assume, for example, the simplest possible case, and that is that the charge density is constant, rho star, if we're in the interior, and it's 0 if we're outside. So I'm just going to assume a uniformly charged sphere. And when I say sphere here, I mean a volume. So technically, to get my language right, I should say a uniformly charged ball. Okay? Because in our language, sphere is just the surface of it, but this is a volume. Okay? All right. So, yes. All right. So because this is uniformly charged, we got a very simple relationship between the total charge of the thing and its volume. And we don't have to go back to physics 1 and remember how to calculate objects from density distributions. It's just the good old volume times the charge density. That formula works when the charge density is constant. So the total charge in this object is given by that. And here we go. All right, so kind of playing the same game we played for the exterior. if we integrate this bad boy, okay. If we integrate this thing over the volume in spherical polar coordinates out to the radius of interest, so maybe we're wanting to go out to here, okay, then we can convert this into a surface integral. This is the same thing we did last time. This time, though, we got to be a little bit careful because when we integrate the volume side, this is just a constant, so we can pull it out. So I'm integrating the volume, but I'm only integrating the volume out to the radius little r. Okay? So my volume is going to be 4/3 pi little r cubed times this constant factor. Okay? But 4/3 pi rho star, that's starting to look a lot like this. Except this is big R cubed and this is little r cubed. But that's okay, we can write it in terms of Q total. And so in the end, this is going to just be Q total over epsilon naught little r cubed over big R cubed. Okay. If you're confused, just take this expression, plug it in for Q total, and you'll see you get right back that. Okay, now we do this integral. We're integrating over the area. The electric field is perpendicular to the area, so this dot product simplifies, and this actually just becomes the magnitude of the electric field times the area of the circle of radius r. So this is going to be 4 pi little r squared times the magnitude of the electric field in the interior, and then we can say that that's equal to Q total over epsilon naught r cubed over big R cubed. Solving that for E interior, we're just going to have Q total over 4 pi epsilon naught. The r squared is going to make 3 of those go away. Boom. Okay. So our interior solution for the electric field is given by that expression. Notice, totally different r dependence than the exterior. The exterior falls off as 1 over r squared. The interior solution actually grows with r. Don't pay attention to that r cubed factor. That's just a constant. Okay, intuitively this should make sense. As you move away from the center, you're encompassing more and more charge. So the electric field is kind of growing. In fact, you're accumulating more charge than you're losing in the normal 1 over r squared fall off. Once you leave the sphere, as you move away, you don't get any more charge, but you get further and further away from the charge, and that's where you see your 1 over r squared fall off. Okay? All right, last but not least, check it out. If I take this bad boy and I evaluate it at capital R, what do you notice? Yeah, it agrees with it matches up nicely to the exterior solution. So the interior solution, when little r is equal to big R, is exactly the same as the exterior solution when little r is equal to big R. So these interior and exterior solutions match, which is what we would expect. Sweat a little bit. Okay, so the key thing that I want you to realize is there's some matching that happens, but in order to solve the interior, you really have to know something about the distribution. Okay? It's going to be harder in GR. But there's still going to be a point where we have to provide some model of the interior based on which we solve for the geometry. And we'll get to that point, but the steps of the rest of this are going to be more complicated. Okay, so going back to GR. The first horrible thing that we learned is that T mu nu is not equal 0. We're inside the thing. We're not outside. And this means that we don't get to use that really slick form of Einstein's equation. We wrote it in trace reverse form so that it was r mu nu equals a bunch of stuff in terms of t, and since t was 0, the whole right-hand side was 0, and we just solved r mu nu equals 0. So rather, what we've got to do is actually solve Einstein's equations in its legit form. And so coming back to what it really looks like. Okay. This thing on the left is just defined to be this particular combination of the Ricci tensor and the Ricci scalar and the metric. This thing is called the Einstein tensor. And one of the nice features of Mathematica, the package is that if you feed it a metric, you can just say calculate that. And it's basically giving you the left-hand side of Einstein's equation. Okay? Now, the analog of providing information about the charge distribution here is providing information about the source, T mu nu. Okay? So we're going to have to say some things about what we're going to use as a source. If we assume, oh yeah, even before we do that. So the first thing that we're going to do is we're going to assume spherical symmetry. Now here's the cool thing. You ready? Sarah, you ready? Yes. Well, I was checking because, I mean, okay, ready? Here we go. We have a different Einstein equation to solve now than we did before. But we didn't even use Einstein's equation until today. Everything we did in the last lecture, we never even used Einstein's equation. That means we can literally repeat all of those steps, even in the interior. Okay? Which means, without any further ado, that we can start with a metric of this form. And this was literally our starting point today. Because to get the metric from its 10 unknown functions of 4 coordinates down to this form only required spherical symmetry and just making use of coordinate redefinitions. Okay? Now, today, in the exterior case, we massaged Einstein's equation and found that we could get this thing to be time independent. We cannot do that for the interior. So we're going to do something different. Alex?
Do you not have to match the interior and exterior solutions? Because how can an interior solution depend on T and the exterior not?
Oh, I mean, in this, how can the, well, it was what I was saying, like, you can literally have a round object that's growing, but the geometry outside of it is not going to change with time. It's just that's the consequence. Okay? I mean, what will change is the region which you call inside and outside. So that you have to be careful about. But if you pick a point which is always outside, it will not change with time. Okay? Okay, now I'm going to reiterate this because what I'm about to do might seem cheap. In the exterior case, we could show that it was, you could get it in a time-independent form. For the interior case, we are going to assume time independence. Now, what's key about that is that when you make an assumption, you can solve the differential equations, but you need to check if your assumption was consistent. And that is the key observation we'll find at the end. Okay? So I'm assuming T independence, I'm not proving it. But that being said, our metric now takes this form. Okay? And let's see, look at, yeah, all my notation is right. Okay, so the two functions that we would need to find in this interior solution now are alpha of r and beta of r. And just for simplicity, let me actually write down what the metric looks like, because we're going to get in the guts of this. So if I write down the metric instead of the line element, I'm going to have minus e to the 2 alpha, e to the 2 beta, r squared and r squared sine squared theta. And that tells me that if I calculate the inverse metric, which is easy because it's diagonal, then the signs of the exponents swap. So in our analysis, we have to be very careful when we're using the metric and when we're using the inverse metric, and that's going to be represented in sometimes the exponents are positive and sometimes the exponents are negative. And when that happens, it's largely because of using the inverse metric. Okay, now, I'm going to have to get rid of some of this junk over here. All of it. Okay, so now what we can do is take that metric, that sweet little metric, and shove it into Mathematica, the great package, to be precise. And we can say, hey, Mathematica, what is the Einstein tensor that you get from this thing? Okay? And it turns out that the Einstein tensor is actually symmetric. It didn't have to be, but it is. So we only have 4 components of the Einstein tensor to futz with. Okay? That is not always guaranteed. You know, diagonal metrics do not have to give you diagonal Einstein tensors. The real magic of this is that it's not only diagonal, but it only depends on r and then theta through that standard spherical term. Okay, so I want to solve this differential equation, and what I've done now is I have taken the metric with these unknown functions, shoved it in and gotten expressions for the components of the left-hand side. Now I have to say something about the right-hand side. In the exterior case, I kept saying, what do we set it equal to? 0. Well, now we're not going to set it equal to 0. We're going to set it equal to this. But I have to tell you what t mu nu we're going to use. Okay? So for t mu nu, we're going to assume a perfect fluid. So a perfect fluid source, and therefore, and this is where you get the money for your efforts, you know that the energy momentum tensor of a perfect fluid can be written in that form. Okay? Everybody remember that expression? Yes? Good. Awesome. Okay? So, now, a couple of manipulations that we can do. We might like to know what is the form of the 4 velocity. What does 4 velocity look like? Say it louder, Katie.
Gamma, gamma, V.
U mu is gamma, gamma, V. No, sir! Ma'am. Sorry. And you said exactly what I wanted you to say. No, no, no. You said the right thing. This is true for flat space. We ain't on flat space anymore. We don't actually know what U mu looks like. Don't assume it looks like the flat space form. Okay? So, what does it look like? Well, we can kind of figure it out from the following. One thing that doesn't care about whether you're on flat space or curved space is the square of the 4 velocity. It's still equal to -1. And that's just because of the way it's defined. The 4 velocity is the derivative with respect to the path length. But then when you square it, it's the path length over the path length. So it's just 1. Okay? Actually writing down what that would look like would be like that. That's just using the metric to raise that thing. Or, yeah, using the metric to raise that guy, sorry. Okay? But now we're going to make an assumption. Assume overall rest frame of source. That is, let us assume that whatever object we're studying, overall we're at rest in it. We're not moving towards or away from the center. Okay, so it's, as a fluid source, it's just sitting still in our rest frame. What that means is that whatever the form of the 4 velocity, the spatial components should be 0. Because the spatial components, whatever form they take, they are describing the spatial motion. And we're assuming zero spatial motion. But what that means is that when I do the sum over mu and nu, the only terms that contribute here are the zero terms. So this is going to be G00, U0, U0. Okay? But G00 is that right there. It's the 0, 0 component of the inverse metric. Okay? So this is going to be minus e to the minus 2 alpha U0, U0. But that thing has to be equal to minus 1. So here's the answer that Katie should have given. In no way, in shape, or form would anybody have guessed this. U0 is equal to what?
E to the 2.
E
to the 2.
alpha.
E to the alpha.
Plus
yeah.
or minus?
Hmm?
Plus or minus?
Plus or minus?
Just
Or
plus.
plus. So the time-lag component's got to be positive. Okay? So we found the form of u sub 0. The u sub i's are 0 because we're assuming we're in the rest frames. All right? And what we can do now is we can come to our energy momentum tensor and write it using this formula because we know u mu and u nu now. Okay. So in the overall rest frame of the fluid, we have the following form of our energy momentum tensor. We have e to the 2 alpha times the times the mass density, e to the 2 beta times the pressure, r squared times the pressure, and r squared sine squared theta times the pressure. Okay. We still don't know mass density rho and pressure p, but the form of this thing is as follows. Okay? And you're picking up the e to the 2 beta because this expression involves the entire metric in that term. And of course, the entire metric does have the e to the 2 beta. Okay, now what we can do is we can take the Einstein tensor, which we got from Mathematica. I mean, supposing we've got this from Mathematica. We can take each piece of it, and notice I said there's only 4 non-zero pieces. Take each of them and set them equal to 8 pi g times the corresponding piece here. So that's the TT term, the RR, theta, theta, phi, phi. And that will give us 4 differential equations. They're differential equations because the right-hand side involves the same unknown functions that are going to come out of putting this metric into Mathematica and getting the Einstein tensor. Okay, so let's start looking at some of these. Now, I'm going to simplify this a little bit more. And maybe I can get rid of this. Simplify this a little bit more by making the following definition. Now, this is motivated by the Schwarzschild solution on the exterior that we got, and the idea that the interior solution is going to have to match to that at the radius. So what I'm about to write down seems quite liberal, but it's very well motivated. Instead of working with this thing right here, okay, this is currently an unknown, I am going to instead work in terms of the following unknown. What's up, dog? Okay. Where this mass is sort of a mass function, it's a function of radius. But clearly what we have in mind is that at the edge of the object, this is literally just the mass of the whole object. And in that situation, this term just becomes 1 minus 2gm over r, which is the term we see in the exterior solution. So this is an inspired form, but it's designed to match the exterior solution at r equals big R. Okay. Now, I can treat this thing as an unknown because there's one unknown function of r here and there's one unknown function of r there. It doesn't matter. The form is more convenient here, but there's an unknown on each side. So I can do my analysis in terms of this form of things. And if we take this and we solve it for m in terms of the unknown function beta, then that takes this form. So you can go back and forth. You can work in terms of beta, or you can work in terms of n. It's going to be a lot easier to work in terms of m. And one of the reasons for that is because when we analyze the TT component of Einstein's equation, okay, and one more. Oh shoot! Sorry. I don't know why I wrote these up. They're supposed to be down. None of you corrected them. That's okay. When we write down the TT component of Einstein's equation, again, we're going to take the metric written in terms of this e to the 2 beta, this thing capturing it, and then we're going to grab the TT component of that. Then the differential equation on the left-hand side is going to take this form. Actually, sorry, this is not if we do it in terms of the TT. This is if we do it in terms of alpha and beta. And you'll see the benefit of doing it in terms of m in just a second. Okay, that's what the Einstein equation looks like if you prefer to work in terms of beta. Okay, ugly. If instead of working with this as your metric function, you use this as your your unknown metric function, then the same equation takes the following form. Now, do you understand why we do this? Okay. So that is literally the beta goes to m substitution. You can take this differential equation, and everywhere you see an e to the 2 beta, replace it with that, and it will simplify to that very next one. Okay. I'm sure I'm going to regret erasing this, but too bad. All right, here we go. So close. I actually have 2 pages that I have to get through. All right, so what we can do with this equation is we can integrate it to find m of r. So remember, I haven't told you what rho is yet. This is the mass density, but I haven't explicitly said, here's the way the density changes. So the idea here is that I would give you the mass density, and then you would solve the differential equation. Okay? So to find m, if I give you rho, all we do is integrate both sides. And so this is just going to be 4 pi times the integral from 0 to the position you're actually interested in of the density function. And just like all the physics 1 students hate, we'll be really careful and distinguish between the integration variable and the actual limit of integration. And then our matching condition is just that when we do this integral all the way up to r, for whatever density we're given, that we identify that with the total mass of the object, and that will guarantee that our interior and exterior solutions match up. Okay? I'm going to call this 1. That will be one of 3 key equations that we're going to use to study interior solutions. Okay? Now, notice early on in some stuff I erased, I said, because we used all of this spherical symmetry stuff that we did last time to write down the metric in a really simple form, and then we assumed time independence, and that left us with 2 unknown functions. That's all we're trying to find. This one we replaced with this. Okay? So here you go. Here's an equation for one of the 2 unknowns. Now, it's not the whole story. Next up, if we consider, and I think I could do this here. Yeah, I'll do this here. Next up, if we consider the RR term, then in the alpha beta language, it's going to end up looking like this. Where prime is derivative with respect to r, it's the only thing we're taking derivatives with respect to. And that's the P, the pressure P. So the Einstein tensor contribution GRR, the 8 pi g times the energy momentum tensor. And now what we can do is, again, instead of beta, write this in terms of m. So take this thing and plug it in everywhere. And then this equation becomes that the derivative of alpha is g times mr plus 4 pi g r cubed p over r times the quantity r minus 2g times the function m of r. Okay. Nothing inspiring about that. Can't really do anything to make it pretty. Sorry. We'll move on. I'm going to call that 2. And I'll explain 1, 2, and 3 in just a moment. Okay, now we could go on writing down, components of Einstein's equation, look at g theta theta, look at g phi phi. But it turns out, and this is again not obvious at all, to get the last thing that we need, it's actually easier and quicker and cleaner to just skip Einstein's equations and go to energy momentum conservation. Okay? So energy momentum conservation in the covariant form takes the following. It's that the covariant derivative of the energy momentum tensor is equal to 0. This guy secretly encodes both energy and linear momentum and angular momentum conservation for that matter. It's got all the love in there. But if you take this thing and you consider the nu equals r term, that is, you take the one free index and make it the radial index, then this gives you an equation that looks like this. Rho plus p d alpha dr, which I'm also calling alpha prime, is minus dp dr. Okay? And then, if I combine this with the RR term from Einstein's equation, then I can get to an expression that looks like the following. dP dr equals minus rho plus p quantity g m of r plus 4 pi g r cubed p over r times quantity r minus 2g m of r. Bam. Okay. This expression, which I'm going to lovingly call 3, notice I am free to use 3 and 2 to solve something because although I got 3 from energy momentum conservation in conjunction with this still has extra information over what this equation has because it's got the energy momentum stuff in it. Okay? So really and truthfully, these are all good tools. These 3 equations I can use to solve for the interior solution. I'm going to show you how to do that in a second. This guy is so famous he gets a name. He's called the Tolman-Oppenheimer-Volkoff equation. I'm not even going to bother spelling those because I'll get them wrong and it will run out of time. This is how we use it. You ready? Start with a mass density. So you give me a mass density. So tell me how the mass density varies with radial position. You got to start somewhere. It's like giving me the charge density. What's interesting is that you can't independently give me the mass density and the pressure. One is determined by the other in conjunction with the geometry. So you're over-determining things if you try and tell me the mass density and the pressure. Okay? So you give me the mass density. We have assumed spherical symmetry. We have assumed time independence. We've assumed a perfect fluid. We assume we're in a thrust frame. But with all those assumptions, starting with this, we can A, use 1, that is that equation up there, to get the function m of r. That's pretty easy. We just integrate the mass density. Okay? The next step, now that we have m, we can go to this equation and now squint your eyes and look at the knowns and unknowns. The mass density, we know, that's what we start with. M, we just figured out from the first step. So the only unknown in this equation is P, the pressure. So now we use 3 to get P. Okay? Once we have P, 2 allows us to solve for the last unknown function alpha. This is that other piece of the metric which we haven't figured out yet. We can solve for this by integrating the right-hand side here because we know m and we know p. Okay? So lastly, we use 2 to get alpha. Okay. You can't skip this step. Like you might say, I didn't care about the pressure. All I wanted to know was the geometry. Well, unfortunately, you can't get this function without knowing p. So you have to go through this intermediate step of solving for the pressure, and then it informs the rest of the geometry. Okay?
Why would you use that one instead? That makes sense.
Which one? This one?
The del mu t mu nu 0.
Oh. To get alpha?
Because you already have the information from 2 buried in 3 somewhere, right?
Yeah, you could use that. That would be fine. I don't see. Oh, yeah. Well, I mean, you could use this, but this is the derivative of the pressure.
Yeah.
I mean, yeah. Once you have the pressure, you could calculate the derivative. Yeah, you could do that. That would be fine. That would be fine. There's probably, I mean, honestly, I haven't gone through too many of these solutions. There's probably a reason why that's the preferred form. So, but, you know, in your homework assignment, you're welcome to play with that one. Okay? But I will be giving you a homework assignment. Okay, we're late. You guys want to see it or no? It's short. It's an example. Yeah! Oh, man. I should have said on the front row. People are going to hate you. Can I blaze through it? Because then we're done. Then we're done. Okay, I need to blaze through it. So let me blaze through it. And it's good because it's a concrete example of solving this thing with these 3 things.
It gives Adrian a longer lecture to watch.
Yeah, that's true. Yeah. Yeah.
Yeah.
Poor Adrian. Okay, here we go. I'm gonna really crush through it quickly because the end is the punchline. So here we go. I wish I had written 3 over there, but whatever. Here we go. Example. So let us do an example that is as close to what we did for electromagnetism as possible. Let us assume a constant mass density. Okay? So rho of r is going to be a constant rho star if you're on the interior and 0 if you're outside. Okay? That's our mass density distribution. Pretty boring. Here we go. Step A. This is pretty easy. Okay. Step A, we just integrate the mass density. You're integrating a constant times r squared. There are worse integrals out there. From this, we can, if we would like, find the form of the metric coefficient, which now takes the form 1 minus 8 pi g rho star r squared over 3 to the minus 1. Step B, we go to good old Tolman, Oppenheimer, Volkov, more affectionately the TOV equation. Plugging in what we know. And remember at the end of this, the only unknown should be the pressure that we are under, because we're under pressure. Okay, after what in my notes I call a little work, you can solve this with pressure. Yeah, I know.
Obviously, it should follow.
Well, no, I mean, look, at this point it's pure math. Like, I'm not going to do it. Like, it's pure math. It's a differential equation in one variable, and you have to solve it. But if you do, you can do the thing that physicists love to do, which is give you the solution and then go verify that this is a solution of the differential equation, because we never solve differential equations. We're just like, oh, I know the answer to that. You know, you just check it. Anyway, should probably just shut up. But I have to teach a class. Okay, so the solution is, here we go. It's a pretty simple solution. Nothing too cray-cray here. Minus 2gm r squared over the square root of r cubed minus 2gm little r squared minus 3 times the radius square root r minus 2gm. That is the form of the pressure in the interior.
Beautiful.
Which you probably could have guessed. If I gave you enough time. I reckon it's rho star times some stuff. Okay? Anyway, all right. But nonetheless, like it's kind of weird because it's in terms of a lot of big R's, but the little r dependence is there and there. Everything else is just constants. Okay? So that is that. And then lastly, for C, if we solve for e to the alpha, then this is just going to become 3/2 1 minus 2gm over big R to the 1/2 minus 1/2 1 minus 2gm little r squared over big R cubed to the 1/2, where of course this too is the interior. Okay, but who's the lucky candidate? What does this become if little r is equal to big R? So if little r is equal to big R, this is r squared over r cubed, so that's just 1 over r. These two terms are the same. 3/2 minus 1/2 is 1. And so e to the alpha becomes 1 minus 2gm over r to the 1/2. So e to the 2 alpha is that, which is exactly what we got for the exterior. So our interior geometry matches nicely to the exterior geometry, at least this component, and then the beta component naturally matches because that we enforced with the mass condition. Okay, that's it. That's the solution. That is the solution to this interior. Again, under the assumption of a constant or a uniform mass density. So you now have the m function, which if you prefer to express it in terms of the beta function, it doesn't matter. Pick your poison. You've got the pressure if you wanted to know it. Maybe you didn't want to know it. And then you've got the rest of the geometry. Here's the important observation. You ready? Consider this guy right here. There's some very interesting stuff going on. Observation 1. This is not entirely obvious, but the pressure actually increases with decreasing radius. Okay? Does that make sense?
Yes.
Yeah, it does. Like the further you go into the depths of this thing, the larger the pressure that you're going to experience. Here is the interesting part. The pressure at r equals 0, that's the pressure dead in the center. So take this bad boy and set little r equals to 0. If you set little r equals to 0, notice this is a fraction. And fractions go cray-cray when what goes to 0? When the denominator goes to 0. So the place where we're going to have the highest pressure, that's at the center, that we might as well look there. The pressure is actually going to diverge if the denominator vanishes. And what you can show is that this blows up as the mass goes to 4/9 R over G. That is, the mass of the whole thing goes to this value, where this is the radius of the whole thing, from below. Okay. If the mass is less than this, the pressure isn't going to diverge at the origin. But if the pressure gets to that value, or any higher value, then the pressure at the center is infinite. Okay? That's not consistent. I mean, you can't have an infinite pressure.
Sounds like a black hole to me.
Why is this not a black hole? This thing is extended. We're inside of the thing. I mean, black hole's a different thing. So we have encountered an inconsistency. We have found that in a certain situation, that is, if the mass, now again, this is based on our assumption of constant density, but if the mass in comparison to the radius, if the mass is too big, then the pressure at the center is going to infinity, which can't physically happen. What is that telling us? Kind of what you're saying. What was the thing I said we would have to do at the end of solving the problem? Check your assumption. What was your assumption?
Time independent.
That it was time independent. So what we're going to find is, if the mass is too big, there's no way this thing can sit there time independent. It has to evolve with time. Now, if it evolves with time, what's it going to do?
Spin.
Well, there's only gravity. Right now, we've only got gravity in the story. What is gravity trying to do to this ball of stuff? Squeeze it. Well, as you squeeze it, R is only getting smaller, and M isn't changing. So this is only going to be a continued problem. Okay? So that's going to continue to evolve with time. And when we come back next time, we'll talk about where it's going to end up. Sorry for keeping me so late, but we got to where we need to go. Next time, black holes. It's e to the 2 alpha because I erased the 1/2 there. There was a 1/2, and then I put the 2 and erased the 1/2. No, because right now, and we're going to talk about that next time, right now I've only assumed gravity. But stars have other forces come into play. So to figure out whether a real object, we have to think about those other forces, and that's where that limit is going to come, the Chandrasekhar limit.
Do you not
Which
count
is not
up
that
1,
limit,
3,
it's
2?
a little bit different.
Yeah, then what's the point of calling them 1, 3, and 2 if you use them in that order?
Yes,
Why not just call it 1, 2, 3? So 1, 2, 3, and ABC line up. Well, what have I been taught since Daddy Descartes?
That you count up like 1, 3, 2.
No, you do not. You count up.
Wow,
Hey, Avery, you said
sounds in theory.
Yeah.
Why are the equations 1, 3, 2?
Sorry.